Hey everybody, your Friendly Math Tutor here. We are now going to move on to Section 1, Part B. This is the calculator portion of the MCQ of our AP Calc BC test. So let's jump right in here with the first one, which on this section is number 76. They want to know, for what values does this series converge? So one thing we have to be able to do is recognize when something is geometric, even when it doesn't really look like it. So we're going to kind of mess with this a little bit. So one thing we can do is on the bottom, this addition of exponents can be broken up in 2 to the 2n times 2 to the first. And then this 2 to the first is really on the bottom, so that's like a 1/2 that I can bring out in front. And then I have k to the n. And then this 2 to the 2n, well, that's the same as 2 squared to the n, because it's power to a power you multiply. So that 2 squared is 4. And now I'm at where I want to be, because now I can think of this as k over 4 all to the n, and I've got my geometric series. All right, so geometric series is when you generally have something just raised to the n. And the base here, the k over 4, that is what we call our common ratio. And we need to know that if it's geometric, then the common ratio will always, the geometric series will always converge when the common ratio is between -1 and 1. All right, so if I simply just multiply through by 4, I get -4 is less than k, which is less than 4. And that is my answer, so that's D. We do not have to test the endpoints. I mean, obviously the answers, we don't have to test the endpoints. But the reason that we don't have to test the endpoints is because it's geometric. Geometric series is not going to converge at its endpoints. Its endpoints give you these just like diverging series. And that's already kind of like known ahead of time. So you don't ever have to test the endpoints for geometric. That's just to help you maybe in another problem. But in this one, it doesn't really matter because we clearly, D is the only one that works. Okay. All right, number 77. So what we have here is on what intervals is the graph concave up? So we always got to question, what type of graph are we looking at? We are looking at the graph of the derivative, all right? And we want to know where the original is concave up. So f is concave up. I'll do it like this, concave up. When, I'll jump to double prime first. When, whoops. All right, I think we're good now. Okay, f prime and f double prime. Okay, well, if I want something to be concave up, it means I went up f double prime to just be positive. And in order for f double prime to be positive, I want f prime to be increasing. Because when a function is increasing, its derivative is positive. So if I work backwards, if the second derivative needs to be positive, then the first derivative needs to be increasing, which also means the original is concave up. So these are all equivalent statements. So I want to use the one that's most appropriate. Well, that is the middle one because we are looking at the graph of f prime. So I want that to be increasing. Well, that's happening here, and it's happening here. So that's between 2 and 5, and also between 8 and 11, which is answer choice E. On we go to number 78. We got the old ladder problem here. So we've got a 20-foot ladder leaning against a wall. It's sliding away at a rate. All right, so this is our typical ladder problem. So we should know in a ladder problem that as the ladder falls, this distance here is getting longer, this distance here is getting shorter, and this distance here is never changing because it's the ladder itself. And then it's just Pythagorean theorem. So it's x squared plus y squared equals 20 squared. And then derivative, 2x, derivative with respect to time, 2x dx dt plus 2y dy dt. And who cares what 20 squared is? The derivative of it is 0. So I can divide these 2's out because I have 0 on the other side that I could also divide by 2, and it'll stay 0. Now I got to figure some things out. X. X is the distance. It's this length at a specific moment. So how fast is the bottom ladder moving away? When the top of the ladder is 10 feet. So that's when this is 10. So I have to find x using the Pythagorean theorem. So if I sub these in, I will do 20 squared minus 10 squared. And I will take the square root of that. This is calculator. And I'm going to see that x is 17.3205. So that's what I'm going to use for x. dx dt, that's the rate at which it's moving away from the wall. It's sliding down at 2, but the rate at which it's moving away is what we're looking for. So dx dt. Y is this 10. And dy dt is the rate at which it's sliding down the wall. Well, that's 2. So we need to make a negative 2 here. All right, well, this is negative 20. So when I add it to the other side, I'm going to get positive 20. So I get this number times dx dt is 20. So I'm just going to do 20 divided by that number. And it gives me 1.155. It's obviously feet per second. And that is answer choice B. All right, as we keep moving here, we are on number 79 of the calculator portion of the MCQ for our BC practice test. We've got this function, which are the following intervals for which f is decreasing. I think we could just graph this. Or we could find the derivative and graph that. But if we want to know its calculator and we want to know the intervals for which it's decreasing, let's just graph that function. So I'm going to go to the y equals, and I'm going to put in e to the x cosine x. And then I am going to go to window, and I'm going to make my window from 0 to 2 pi. And the other thing that I'm going to do is I'm going to make sure that I'm in radian mode. If you're doing any kind of calculus and that's all you're doing, you should always be in radian mode. But I got to make sure that mine is because I do a lot of different things. Okay, so now we go to graph. And my graph looks like this. And we want to know where it is decreasing. So I'm going to switch colors here. So this function is clearly decreasing from this relative max till we get to this relative min. All right? And I can find those values. So this first value, I will go to second trace, which is our calc button, our calculate button, and I'm going to look for a maximum. So I'm going to hit maximum. It wants left bound. So left bound, I will put somewhere here, and right bound, I will try to get on the other side of that, which is like here, and I hit enter, enter, and I get 0.78. That tells me that it's either C or D. So then I need to find my minimum. So if I go to my second calc again, and I'm going to do minimum, and I'm going to put my left bound like here and my right bound here, and that is going to tell me that it is 3.927. So therefore the answer is C. You could have found the derivative and graphed that and then found where the derivative was below the x-axis. But I don't see why we would do that because like taking the derivative of this would just take some time. So you might as well just jump right to the calculator. As long as you know how to find maximum and minimums, you're good to go. You can pretty much answer this without doing any actual calculus. On to number 80. So we got these parametric equations. Which of the following is the equation of the tangent line at the curve where t equals 2? So anytime you're doing an equation of a tangent line, or anytime you're doing an equation of a line, going back to pre-algebra and algebra, I need a point and a slope. Well, to get my point, I can simply just find, I can just plug in 2 or substitute in 2 for my x and y. That should give me, if I plug into here, I get 12 for the x. Yeah. And if I plug into here, I get -8. So that's our point. Okay. Now our slope. Our slope is going to be dy dx, right? But dy dx is really dy dt over dx dt. Now, this is calculator, so you really could evaluate each of these at 2. But honestly, these derivatives are so easy. The derivative of, dy dt is 3t squared minus 8. And dx dt is 6t squared minus 2t. And then when I plug in 2, so I'm really... looks like this. I'm making t equal to 2. I get 12 minus 8 is 4. And I get 24 minus 4, which is 20. So that's 1/5. Now, we could use point slope and then rearrange it to get one of these. All right. But hopefully, if we are in a BC Calc class, we can look at these and tell that C, D, and E do not have a slope of 1/5, because when you're in AX plus BY equals C form, -A over B is the slope. That's if we just like rearrange this to get it in the slope-intercept form. And only A and B give us 1/5. And then I'll just plug in 12 and -8 into just one of them. So 12 minus 5 times -8, that doesn't, or no, does that work? Yeah, it does. 12 plus, oh yeah, my bad. 12 plus 40 is 52, so that works. You don't get 26. Again, you could do, if this were open-ended, you would do it this way. You would do y plus 8 equals 1/5 times x minus 12. Then you distribute, or you can multiply through by 5. You'd have to get the x's and y's on both sides. It'd just be a little bit of extra work. I find it easy to just like kind of use your answers and the level of math that we're doing. Hopefully we can do those like quick things in our head and kind of use the answer to meet us kind of where we are. All right, number 81. Let's see if I can make this one a little bit bigger. Okay. So we got the graph of the velocity here, all right? And we want to know which of the following could be the graph of the position. Well, what I notice is that I have 2 critical points here, and I have a negative velocity, a positive velocity, and a negative velocity, all right? Which means our position should be decreasing, then increasing, then decreasing. All right, so that gets rid of A, and that's it. Okay, so then I notice that I should, if I'm going from a negative to a positive, I should have a minimum, a relative minimum, somewhere between 0 and 1. So this relative minimum is at 1, so that's out. This one works. This one works. This one does not, because I have a derivative at 0. Like the value of the derivative is 0, not undefined like this is. So that one's out. Now we're down to C and D. And what I then finally have is my relative maximum going from positive to negative should be at 4. And if I go 1, 2, 3, 4, that doesn't work here. 1, 2, 3, 4, that does work here. All right, so my minimum and maximum, decreasing, increasing, decreasing, all works out nicely with C. All right, we are moving. Let's take a look at number 82. So we got another velocity with parametric equations. Which of the following is the distance traveled by the particle along the path? All right, here we just have to know our formula. So total distance is going to be the integral of speed. And speed is just our arc length formula, all right? Or actually, my bad. What we're finding is the arc length, because that's the distance traveled along the path. And the way you find arc length in parametric is the integral of the speed. And the speed is the magnitude of the velocity. So that is the square root of dx dt squared. So that is e to the t sine t squared plus dy dt squared. So that's e to the t cosine t squared dt. This is calculator, so you should just be putting it in just like this. Okay, so I'm going to show you two ways to do this. This one is interesting because it's calculator, but they gave the answers in terms of E, so you could make an argument either way. So if you do this, I will do this really quickly. You get that minus, you get like 4.67, and then you can figure out which answer is equal to that, which is C. If you're, I mean, it's not that hard because like E is definitely not 4.67. E squared minus 1, I guess that could be. E squared plus 1 is definitely way bigger than that, and E squared plus E plus 1 is way bigger than that. So you're really only checking these two, and it turns out that C is that number. So option 1 is to just throw this in the calculator, but then you got to figure out which one of these is that decimal. The other option is this one simplifies nicely, especially if I can take some shortcuts. So I can kind of talk this through. This is e to the 2t and e to the 2t that I can factor out. And this is sine squared plus cosine squared, and that's just 1. So then I have the square root of e to the 2t, which is just e to the t. So it just works out really nicely because the antiderivative of e to the t is e to the t. And then I'm evaluating that from 1 to 2. So that's just e squared minus e. And when I factor out the e, I get letter C. So it's really up to you. If they were all decimals, then calculator would be best. Or if it were non-calculator, then obviously you would have to do it this way. But here you kind of have the option. All right. On to number 83. All right, so which of the statements must be true? So what we have to do is kind of understand just a couple things about when this is actually going to converge. So this, if this series converges, then we know that P is greater than 1. Yeah. So if I look at A, well, A is going to simplify to the sum, n over n to the p is 1 over n to the p minus 1. And that's just, I get that just from subtracting. Really, I get 1 minus p, but then when I move it to the bottom, it becomes like I've switched the signs. And the thing is, imagine this were just like 1.1. Well, 1.1 minus 1 is now less than 1, so that doesn't have to converge. It must be true. So that one's gone. This one is the summation of 1 over n to the p minus 2. All right, well, that doesn't have to be true because, like, p, again, p could be like 2.4, right? 2.4 minus 2 is 0.4, and now I'm back to less than 1. So, again, it doesn't have to converge. Well, C, what ends up happening is I have this thing that converges, and then I multiply by the ln of n on the bottom. Well, the ln of n is definitely a positive number, and that's bigger than 1, especially by the time I get past 3. And when I multiply the denominator by a positive number bigger than 1, the denominator gets bigger, which means the fraction gets smaller. So this is the direct comparison test. If I know that 1 over n to the p converges, then something that's smaller than it has to also converge. And what ends up happening is both d and e make a smaller fraction, which also should converge, but they say diverge. So that's why they are incorrect. All right, on we move to number 84. So a particle moves on the x-axis with this velocity. Which of the following must be true? The velocity of the particle is strictly decreasing, acceleration, and it's speeding up. Okay, I think that we just need the graph of the velocity. And so if I do that, it ends up looking something like this if you just throw this in the calculator. This value is 2. And this value is 3. So everything is on the interval 2 to 3. So we are just looking at this portion of the graph. This can help us answer everything. Okay. So velocity is strictly decreasing. Well, this is the velocity graph. So velocity is definitely moving downward through this interval. So 1 is correct. The acceleration of the particle is strictly decreasing. Okay. Well, the acceleration, if that's decreasing, let's think about that. So the acceleration is the derivative of velocity, and if this acceleration is decreasing, then the derivative of acceleration would be negative, and that derivative would be the second derivative of velocity. So if we're looking at the velocity graph, for that derivative to be negative, the velocity would have to be concave down, but here this is concave up. So this is wrong. So it could be this one, and it can't be this one. So it all depends on number 3. The particle is speeding up. Well, a particle is speeding up when there's a sign match between the velocity and acceleration. So let's think about the velocity here is negative because it's below the x-axis, and the acceleration is negative because the velocity is decreasing, which we already established in number 1. So both of them are negative. So that is true. So it ends up being E. Another way to look at it is a quicker way to just kind of, if you wanted to just like memorize this, if you're looking at a velocity graph, anytime you're moving away from the x-axis, it's speeding up, and anytime you're moving toward the x-axis, it's slowing down. But again, that's because there's either a sign match or a sign difference. So it's not just like blind memorization, but if you just know to look for that really quickly, it can save a little bit of time. Okay, let's move on to number 85. Here we have the position of the particle is given by these equations. Which of the following is dy dt at time t equals 2? All right, so if I want dy dt, I want to take the derivative of this with respect to time. So dy dt is equal to, well, the derivative of this is x squared dx dt plus 6x dx dt. And then the derivative of that is 0. And if I want to find it at time t equals 2, all right, I want dy dt. We're really doing at t equal to 2. And then I'm going to figure out what x and dx dt are, all right? Well, at time 2, if I do 2 times 2 is 4, 4 plus 1 is 5, x is 5. So this is 25. Now dx dt is the derivative of this. Well, that's just 2 times 2 plus 6 times 5 times 2. So I get 50 plus 60. That's 110. So 85 is D. All right, 86. Let R be the region enclosed by these graphs. Y equals root x. If you can throw these into a graph, that will be important. You're going to do this, and then you're going to see that the other one is kind of like this. This one is root x, and this one is e to the negative x. It's enclosed over here because it's enclosed by the graphs and the line y equals 0. I feel like that... I think this is supposed to be x equals 0. I think that's a typo. Because if they definitely want it to be this area over here. So this is x equals 0. Y equals 0 is the x-axis, and that really wouldn't make sense. So let's make that correction. So the cross-sections are semicircles. What's the volume of the solid? So what I need to do is find this intersection point. This, again, just put it in the calculator. So I'll show you a nice, easy way to do this. So put this as your y1 and make this one your y2. And then, whoops, make this one your y2. And then what you're going to do is just find the intersection in the calculator. That's your second calc. You basically, there's only one intersection here. So you just do second calc, and then you do intersection, and then just like enter, enter, enter. And you'll figure out that that point is 0.426. All right. Now we're going to set up the integral. All right, so the semicircles are perpendicular to the x-axis. So this right here represents the diameter. So I'm going to be taking the integral. And if I think about the way that we get the area of a semicircle, first of all, it's 1/2 of pi r squared. So I'm going to put a 1/2 pi out here. And now I'm going to put the radius squared in here. Well, the radius squared is the diameter is the top function minus the bottom function. All right, so it's actually y1 minus y2 over 2. All right, so this y1 minus y2 is the diameter, and then I have to divide that by 2 to get the radius, and then I have to square it. And then I have my dx, and then I'm integrating from 0 to 0.426. And since we had to use the y equals, since we had to graph it to find the intersection, since you already have these stored in the y equals, you can just do this in the integral. So I do alpha window 4, puts the integral up. And then when you go into the actual like integrand part, if you go to alpha trace, you can go to, you'll have a little menu that comes up where you can put in a y1 and y2, and it'll save you having to type in these functions. And some problems it saves you significant time because you might have to, like these aren't too hard to type in. So again, just a little like shortcut with your calculator. When you do all that and hit enter, we end up getting A. All right, so the key is knowing how to set up the problem, but also if you could do little things in the calculator to just save you a little bit of time, that time adds up and gives you some more time on the even harder questions. All right, we're moving along here. 87. We have this function, and p of x is a second degree Taylor polynomial about x equals 1. The graph of f is shown. which of the following is the value of P? All right, so it's the... All right, so let's think about this. All right, we need P of 1.5. All right, so in general, if we want to find a second degree polynomial for G, that's going to be, let me think about this. All right, that's going to be G of 1 plus G prime of 1 times x minus 1 plus G double prime of 1 times x minus 1 squared over 2 factorial, so over 2. All right, so I do the second degree Taylor polynomial centered at 1. That looks like this. So now I need to find all of these values. So G of 1. Well, G of 1 is plugging 1 into here and here. So I'm integrating from 2 to 1 of this function. All right? That is going to be just the area of this triangle, which is 1 times 4 divided by 2. So that's 2. But I'm integrating backwards, so that's negative 2. So G of 1 is negative 2. Now, G prime of 1. What G prime of 1 represents is just f of 1. Because if I take the derivative of this is the second fundamental theorem of calculus, G prime of x is equal to f of x. So G prime of 1 is f of 1. Well, that's 0, right? Well, that's good. That makes all this just go away. So this is gone. Now G double prime of 1. G double prime is f prime. Well, f prime of 1 is the slope of this line. All right, well, I can just look at this piece of it. I know it goes up 4 and over 1. So the slope is 4. So G double prime of 1 is 4. So I get negative 2 plus 4 over 2 is 2 times x minus 1 squared. So this is my second degree Taylor polynomial, and I want P of 1.5. So I can just do this really quickly. 1.5 minus 1 is 0.5 squared is 0.25 times 2 is 0.5, and negative 2 plus 0.5 is negative 1.5. You could just all do that all in a calculator if you really wanted to, but we all should end up with the answer choice C. All right, that was a pretty challenging problem. They put a lot of the concepts together on that one. I like it. All right, we are getting near the end here, so let's take a look at number 88. So we got another Taylor series. What's the point of intersection of the graphs of f of x and the line x equals 1/2? Okay, so I think they're just having us plug in 1/2, but we're going to need to find it. We need to figure out what this is. So it looks similar to e to the x in a way. So if I start with like e to the x, because again, all we're doing, this is like a fancy intersection of line. This is just plugging in 1/2, all right? But we can't plug in 1/2 to this. I guess we could. You could probably do that and then do it for like a decent amount of it and figure out which one is closest. That is an option, but I'm going to do it the more like calculus way. So if e to the x, this looks similar to e to the x. This is e to the x. Right? So it looks like what I'm doing is I'm replacing each x with x squared. You can really see it there. So this is really just e to the x squared, all right? Because this will be x squared. This will become x to the 4th. This will become x to the 6th. So we just needed to figure out that this function was just e to the x squared. And then I just throw that into a calculator. I'm doing e to e to the 0.5 squared, which is just e to the 0.25. So let's do that. And that gives me like 1.284, which is A. All right, again, another option. If you don't see that this is e to the x and then this is e to the x squared, what you honestly can do is just plug in 1/2. Just do it for a little bit. Let me see what happens. So I'm going to do 1 plus 0.5 squared plus 0.5 to the 4th, and then that one's divided by 2. And I'm going to go one more. Plus 0.5 to the 6th, and then that's divided by 6, because 3 factorial is 6. And that gives me 1.2838. So that's like the only one that's close. So you can definitely do it that way. These are excellent approximations of their functions, even just to the first couple terms. Even though it takes to go to infinity to be exactly equal, it's super, super close just with a few terms. So that's another way you could just go about this, really, if you understand that. All right, number 89. So we got this differentiable function, fx is greater than 0, and the graph is increasing for all values. G of x is the integral of f of x. Which of the following must be true? All right, so g is increasing over the entire x-axis. So if we want to know what g is, then we're going to take g prime. Well, g prime of x is f of x, because it's just the derivative of the integral. Well, f of x is positive. Well, if f of x is positive, then g prime is positive. So then it's always increasing. The graph of g is continuous. Well, g is the integral from 0 to x, and f is differentiable and continuous. So therefore, g just has to be continuous. Yeah, I don't think there's anything more to that. Yeah, if f is continuous and you integrate it, then g is going to be continuous. Okay? And the graph of g is concave up. Well, concavity is the second derivative. Well, the second derivative of g is the first derivative of f. So let's think about that. Well, f is increasing. All right, well, that means f prime is always positive, so g double prime is always positive, so it's always concave up. Turns out to be all three of these, which is E. All right, number 90. So, g is this integral. Which of the following does it have a point of inflection? So, let's take the derivative first. Yeah, let's do the derivative because I don't want to plug this in. So we're going to do the derivative. So this is second fundamental theorem of calculus, the derivative of the integral. They kind of cancel out. I'm going to be plugging in x squared for each t. So the root of x squared is x, so I get e to the negative x. Then I get the sine of 1 over x squared, and then I have to remember chain rule. I have to multiply by the derivative of x squared, which is 2x. So this is g prime. And if I want a point of inflection on the graph, that's when the second derivative is equal to 0. So that's when the derivative of the derivative would equal 0. Well, instead of taking the derivative of this and doing all that work, this is a calculator problem. So I am going to just graph this. So I'll go to the y equals. I am going to do 2x e to the negative x sine of 1 over x squared, or sine of, I'll just do x to the negative 2. And I want from 0.5 to 2. So I go to window, I'm going to change it from 0.5 to 2, and then I'm going to just hit graph, and I'll show you. I got something like this. All right, so I want a point of inflection. which would be this point here, because this is the 0 of the G prime. Wait, let me think about that. That is not correct. No. I thought of that wrong. Okay, so scratch that. All right, rewind a little bit. So forget about that. I want to know when the derivative of the derivative equals 0. So when a derivative of anything equals 0, it's when you have a max or a min. So I'm really looking for this point up here because I have increasing to decreasing, which means the derivative of this goes from positive to negative, which means the second derivative goes from positive to negative, which therefore the original is an inflection point. All right, so I need to find this point. This is just the max value. So I'm going to go to second calc maximum, and I'm going to move my cursor so that my left bound is on the left side of that, and my right bound is on the right side of that. And it should give you 0.814. So I put left bound here, right bound there, and it told me that this value was 0.814. All right, so even I got a little confused there. I was looking for the x-intercept, but no, I don't need the x-intercept. I want the maximum or minimum value of the derivative would be the point of inflection for the original. All right. Okay, we are getting there. We are on number 91 on the MCQ part 2 here, calculator section. So we got a function, the tangent line at x equals e is used to approximate f of 2e, which is the following value of the error resulting from the tangent line approximation. All right, so we just need to, first, we could find f of 2e. Well, that's the ln of 2e. Which you could just use a calculator. I mean, you certainly could do a couple things, but you could simplify that, but why? It's calculator, all right? So we are just gonna find the natural log of 2e, and that is 1.693147. I'm gonna really write it out there, all right? Okay, so that's the actual value. All right, so now I'm going to use the tangent line to approximate that. So what I have is I need my point. So my point is e. Oh, at x equals e. Yeah. I need e, and then I need to plug it in here. Well, the ln of e is 1. All right, so I get e comma 1. That's the point. And then I need to take the derivative. Well, f prime of x is just 1 over x. Whoops, which means the slope is 1 over e. And then if I think of point slope, I just do y minus 1 equals 1 over e times x minus 1. Or sorry, x minus e, my bad. All right, and then I have y equals 1 plus 1 over e. And then I'm going to replace x with 2e. 2e minus e, this is an e. 2e minus e is e. E times 1 over e, I'll put an e here. E times 1 over e is 1, and then 1 plus 1 is 2. So my approximation is 2. Well, the distance, how far off I am, is just 2 minus the 1.69. And that is about 0.306. which really 307, which is D. All right. Here we are on our last problem on this section. So we are using the trapezoidal rule to approximate f of 1. Well, f of 1 is just the integral from 0 to 1, and we're using trapezoidal with 4 subintervals. So I'm going to, try to draw this out. So this is 0 to 1, and if I want 4 subintervals, I'm going to have 0.25, 0.5, and 0.75. And then the way the trapezoidal rule works is you are finding the area of each trapezoid, which is the average of the bases, and the bases are actually going to look like the heights. they are going to be plugging this into the function. And then it's multiplied by the height, which is really the delta x here, which is 0.25. So that 0.25 is going to be part of all of them. So I'm going to factor that out, and the divided by 2 part, that is the average of the bases part of the trapezoid formula. So I can factor that out. And then what I'm doing is I am just now, I'm finding, like, I'm adding the bases up. So it's going to be sine of 0. I know that's 0, but I'm still going to write it out. And then I have 2 of these, because the way this works is this base is part of this trapezoid and this trapezoid. So I get 2 of all the middle ones. So 2 sine of 0.25 plus 2 sine of 0.75. I'll go down here. Then I get plus 2. I skipped. I'll put, this is 0.5 here. And then 2 sine of 0.75. And then when I get to the last base, that is only going to be one of those, so plus the sine of 1. And then you can throw all this into a calculator, and you get about 0.457, which is just D. Yep. All right, that's it. Hope that was helpful.